Okay, so now we're going to turn our attention to solving logarithmic equations. And much as we saw with our experiences with exponential equations, in which there were two basic methods of solving them, right? To either write them both sides of the exponential equation in terms of the same base and then use the one-to-one property of exponential functions, or to use logarithms, right, in order to solve the exponential equations that we could not use the one-to-one property to solve. Much the same way for logarithms and logarithmic equations, we're going to have two basic methods of solving them. And the first one that we're going to look at is using the definition of a logarithm to solve logarithmic equations. And if you notice, the first thing that it says to do is to express the equation in the form log to the base b of m equals constant, right? A constant. So, the first few examples that we're going to do are already going to be in this form, and then we'll see that we might have to do a bit of work first in order to create this form. But regardless, once we have that form, we're going to take that logarithmic equation and write it in its exponential form. Okay, and remembering that logarithms are exponents, right? Base, exponent, result, right? Base, exponent, result. And then we're going to solve for the variable. And then this is extremely important, and this varies from our exponential equation solving experiences. We have to check our proposed solutions in the original equation. And we have to include in the solution set only values for which m is greater than 0. And another way of saying that is include in the solution set only values which are in the domain of any of the logarithms in our original equation. Okay, so let's look at this first example. And it says log to the base 3 of x equals 4. So all I need to do for this one literally is write it in its exponential form. The base is 3, the exponent is 4, the result is x. So x equals 3 to the 4th, and all I have to do is realize that 3 to the 4th is equal to 81, and I have worked, solved this logarithmic equation. Now remember that I have to check my proposed solutions in my original equation, and what I'm checking to see is if I plug 81 into my original equation, will that argument, will what I'm taking the logarithm of, be positive? In other words, is 81 in the domain of log to the base 3 of x? And yes, it is. Now, if I had gotten log to the base 3 of negative 81, well, I know that I cannot take the log base 3 of a negative number, right? In other words, the domain of this logarithmic function is all values x that are strictly greater than 0. Well, 81 is within that interval. And so that proposed solution is, in fact, a valid solution. And we may conclude that x is equal to 81. So for example 14, we do have it in the form logarithm, right, of an expression this time, natural log of 3x plus 4 equals 6, but it does meet that form, right? And for me to write this one in exponential form, I need to remember that the base for the natural log is e, right? So this is going to be e to the 6th equals 3x plus 4. And in order for me to solve for x in this equation, first I'm going to subtract 4 from both sides, right? So I'm going to get e to the 6th minus 4 is equal to 3x. And then I'm going to divide both sides by 3, right? And then I'm going to get that x is equal to e to the 6th minus 4 divided by 3. Now, this is my exact answer, right? And in the homework, it's also going to ask you for problems like this one, for solutions like this one, where you don't get a nice integer answer like 81, right? It's going to ask us to give a decimal approximation to two places. And again, we're going to do that same thing we did before. I'm going to first calculate e to the sixth minus 4, hit enter, and then divide that result by 3. And in doing so, I am much less likely to make a mistake with respect to my order of operations. So e to the sixth minus 4 is, and I'm going to write out all of the decimal places, but you, of course, do not have to do that. You can just leave it up on your calculator display. 399.4287935 divided by 3. All I'm trying to get you to see is that you should do that calculation in the numerator first, hit enter, and then divide by 3. And you will get that this is approximately equal to two decimal places, 133.14. This is your proposed solution at this point, right? One of the reasons that we get a decimal approximation for these problems is so that we can more easily judge whether or not our proposed solution is going to be in the domain of this particular logarithmic function. So if I come back up here and I plug 133.14 times 3 plus 4, I am going to get a number that is greater than 0. Yes? Yes. So this is the solution to two decimal places for this particular logarithmic equation. Okay, so example 15 has log to the base 5 of x squared minus 2x plus 10 equals 2. So this one has the proper form, right? It's a single logarithm equal to a constant. So I need to go ahead and write it in exponential form. So 5 is the base, 2 is the exponent, equals x squared minus 2x plus 10, right? This is why we spent all that time practicing writing logarithms in exponential form. So 5 squared is 25 minus x squared minus 2x plus 10. Okay, so now I have a quadratic equation. And recall that in order to solve a quadratic equation, I first want to go ahead and set it equal to 0. So I'm going to subtract 25 from both sides. And I'm going to get 0 equals x squared minus 2x minus 15. And remember, I need that 0, right? And at this point, you can be certain that these are going to factor, all right? So if you end up with quadratics as a result of solving these logarithmic equations in section 4.4, you're not going to have to use a quadratic formula. So they're going to factor. Now, given that that's true, my task is going to be to find two numbers that multiply to give me negative 15 and add to give me negative 2. And those are going to be, let's see, leading coefficient is 1, so x and x. It's going to be negative 5 and positive 3, right? So then either x minus 5 is equal to 0 or x plus 3 is equal to 0, right? And if I solve this one, I'm going to get x equals 5. And if I solve this one, I'm going to get x equals negative 3, okay? So for this one, I got two proposed solutions. And I'm asking myself, is it the case that if I take both of these or either of these and plug them into the expression in the original logarithm, right? X squared minus 2x plus 10. If I plug in 5, will the result be a positive number? In other words, is 5 within the domain of this particular logarithmic function? Well, let's check to see. So I'm going to check by plugging in 5. 5 squared minus 2 times 5 plus 10 is equal to 25 minus 10 plus 10, which is 25. So this is a valid solution. And now I must do the same for x equals negative 3. So my check there is negative 3 squared minus 2 times negative 3 plus 10. This is equal to 9 plus 6 plus 10, which is equal to 25. And so x equals -3 is also a valid solution. So it's not a question of whether or not your solutions, your proposed solutions, are positive. It's a question of whether or not the argument to the logarithms in the original equation are positive after substitution of your proposed solutions. So just be careful with that idea, okay? Check. Now let's move on to number 16, and it says that the log base 2 of x squared plus 4 is equal to 3. So I do have the form logarithm equal to a constant. The base is 2, the exponent's 3, the result is x squared plus 4. So 2 cubed is 8 equals x squared plus 4. So now I have, again, a quadratic equation, and I'm going to subtract 8 from both sides. So 0 equals x squared minus 4. And this is a difference of perfect squares, right? So it's going to factor to x minus 2 times x plus 2. And then I get that either x minus 2 equals 0 or x plus 2 equals 0, x equals 2, or x equals -2. Again, I must check both of these proposed solutions in the original logarithmic equation, right? I got to check to see if I think of this as being log to the base 2 of x squared plus 4 as a function, is 2 and -2 are 2 and -2 in the domain, right? In other words, if I plug in 2, is this going to remain positive? If I plug in -2, is this going to remain positive? So let's go ahead and check. So for the first x equals 2, let's see, 2 squared plus 4 is 8. Oop, I jumped right to the answer, didn't I? Is 4 plus 4, which is 8. That's positive, right? And then -2 squared plus 4 is equal to 4 plus 4, which is 8, which is also positive. And so both of these proposed solutions are valid solutions for these for this logarithmic equation. Okay, so sometimes though we're going to have to use the properties of logarithms to condense one side of the equation so that it contains a single logarithm, and then we can proceed as we did above, right? So when I was talking in section 4.3 about why we would need to know how to condense logarithms, this is that very reason why we need to be able to do it. So looking at the left-hand side of this equation, I can see that I have the difference of two logarithms, and so I need to condense this difference of two logarithms into a single logarithm. And remember that when I see subtraction with respect to logarithms, it should make me think of division, right? So I'm going to condense this into this logarithmic equation. Log to the base 4 of x plus 2 divided by x minus 1 is equal to 1. Now, a couple things to point out. I'm condensing this difference of two logarithms into a single logarithm, base 4, right? So now my next task is going to be to take this logarithmic equation and write it in exponential form. So remember that my base is 4, the exponent is going to be 1, and the result of raising 4 to the first power is going to be x plus 2 divided by x minus 1. So this logarithmic equation in exponential form is 4 to the first power equals x plus 2 divided by x minus 1. And of course, 4 to the first power is 4, right? And to solve this now rational equation, right? So we've seen that these logarithmic equations can generate as part of the solution quadratics, linear equations, and also rational equations. To solve this rational equation, I'm going to go ahead and multiply both sides by x minus 1. And we're going to divide out, right? And I need to distribute the 4 over the x minus 1. So I'm going to get 4x minus 4 is equal to x plus 2. And now I need to solve this equation. So to do that, I'm going to go ahead and subtract x from both sides. And that's going to give me 3x minus 4 equals 2. And then add 4 to both sides. 3x equals 6. And divide by 3. X equals 2 is my proposed solution. And of course, if that, if I was going too quickly for you there, you can always back it up, right? And listen to it again. So now this is a proposed solution, right? So in order for me to determine whether or not it is in fact a true solution and not extraneous, not one that looks like a solution but it's not, right? I need to check this value of x in both of these logarithms to make sure that the argument or the input stays positive, right? So I'm going to come over here and check that first logarithm, log to the base 4 of x plus 2. And then I'm going to check that second logarithm, log to the base 4 of x minus 1. And what I'm checking to see for both of those logarithms is whether or not x equals 2 is in the domain of those logarithms, right? So what I'm really checking to see is if x plus 2 stays positive for a value of x equals 2, and 2 plus 2 is 4, which is positive, right? And then I need to check to make sure that x minus 1 is positive for a value of x equals 2. And 2 minus 1 is 1, which is positive. And so now I can make the determination that x equals 2 is a valid solution to this logarithmic equation. All right, so now let's look at example 18. In this one, I have the sum of two logarithms, log base 6 of x plus 3 plus log base 6 of x plus 4 equals 1. And I'm going to need to condense these two logarithms, and I see that I have a sum of two logs, and so I know that that is going to give me the logarithm of a product. X plus 3 times x plus 4 equals 1. And then I can rewrite that by expanding x plus 3 times x plus 4, or carrying out that multiplication, right? And I'm going to get x squared plus 4x plus 3x, 7x, plus 3 times 4 is 12, equals 1. And now I have it in the form that I need, right? Single logarithm equal to a constant. So I'm ready now to go ahead and write it in exponential form. The base is 6, the exponent's 1. The result is x squared plus 7x plus 12. Please do not forget this part, right? You have to take this logarithmic equation and put it in exponential form. Base, exponent, result, right? Now we've generated another quadratic equation, and I know that in order to solve a quadratic, I need to set it equal to 0. And then I can also remember that these will factor, right? I promise you that they will. They don't necessarily have to, but they will. So x squared, x and x, right? And then two numbers that multiply to give me 6 and add to give me 7 are plus 1 and plus 6. So then either x plus 1 equals 0 or x plus 6 equals 0. And solving this one, I get x equals negative 1. And solving this one, I get x equals negative 6 as two proposed solutions, right? Now, in order for me to make the determination about whether or not one or both of these are valid solutions, I need to check, right, in both log base 6 of x plus 3 and log base 6 of x plus 4, I need to check both x equals negative 1 and x equals negative 6. So first I'm going to go ahead and check x equals negative 1. And remember, I'm checking to see if I plug in negative 1, will this stay positive? And so negative 1 plus 3 is 2, which is positive. And I have to check it in the other one as well. Negative 1 plus 4 is 3, which is positive. So x equals 1 is in fact a valid solution. Now I need to check x equals negative 6. And negative 6 plus 3 is negative 3. And so this is not positive, right? And so that tells me that because negative 6 caused me, when I plugged it in, to be taking the logarithm of a negative number or a non-positive number, that meant that this is not a valid solution. And so of the two proposed solutions, only one is a valid solution. The other one is referred to as an extraneous solution. It's not actually a solution to the original equation. So it's very important that you check. You can't just assume because it's negative that it won't work. That's not the issue. It's whether or not these expressions inside your logarithms are negative or 0, right? These have to be positive, not these numbers. Okay. Okay, so example 19 looks different, right? I've got logarithms on both sides. But all I need to do is go ahead and add log of x to both sides to result in log of x minus 3 plus log of x is equal to 1. Right? So I just need to go ahead and add it to this side, right? Add log of x to both sides, in other words. Now I have an expression on this side that involves the sum of two logarithms, and I know that I can condense that into a single logarithm, x minus 3 times x, right, equals 1. And then I can go ahead and distribute log of x squared minus 3x equals 1. Okay, so just to recap, I started with this logarithmic equation where I had logs on both sides. I went ahead and added log of x to both sides to get both logarithms on the same side of the equation equal to a constant. And then I used my properties of logarithms to condense this sum of two logarithms into the product, right, the logarithm of a product equal to a constant. And I went ahead and distributed then x times x is x squared and minus 3 times x is 3x. Now I have the form where I have a single logarithm equal to a constant, and I need to remember that this is base 10, right? This is a common logarithm, so I know it's base 10. So that's going to help me when I'm thinking about how to write this in exponential form, right? So the base is 10, the exponent's 1, the result is x squared minus 3x. So now I've got a quadratic equation again, right? So if I subtract 10 from both sides, I'm going to end up with x squared minus 3x minus 10 equals 0, right? And I can do it in that way too, right? The 0 didn't have to stay on the left side, right? I could put it on the right side as well. Now, I need to go ahead and factor this one because it's a quadratic, and I assured you that any quadratic that's a result of solving these logarithmic equations will factor. So I'm going to have x, and I'm looking for two numbers that multiply to give me negative 10 and add to give me negative 3, and those two numbers are going to be negative 5 and positive 2. Always check, right? So x squared plus 2x minus 5x is negative 3x minus 10. So I'm going to get that either x minus 5 equals 0 or x plus 2 equals 0. And if I solve this one, I'm going to get x equals 5. And if I solve this one, I'm going to get x equals negative 2. So now I have to check both of these proposed solutions, right, in my original logarithmic equation. So I'm going to go ahead and basically erase this so that I have room, right? I don't have to scrunch it all up. So I'm going to be looking at my original logarithmic equation and asking whether or not log of x minus 3, right? I think I was doing that in blue, so let me go ahead and do that in blue again. log of x minus 3 and log of x, whether those are both going to be okay in terms of their argument staying positive for the two proposed solutions, x equals 5 and x equals negative 2. Okay, so x equals 5, I'm taking that 5 and plugging it in to x minus 3. That's 5 minus 3, which is 2, which is positive. And then if I plug it in here, x equals 5, right? And that's positive. So x equals 5 is a valid solution. But x equals negative 2 is not, because negative 2 minus 3 is negative 5, and that is not positive. And so this proposed solution is extraneous, and I got one single solution to this logarithmic equation, x equals 5. And then the final example on this page is example 20. And again, I see a situation in which I have two logarithms, right? And they're on opposite sides of the equal sign. So I'm going to go ahead and I'm going to subtract natural log of x from both sides. So I'm going to end up with the natural log of x plus 1 minus the natural log of x is equal to 1. Now I have both logarithms on the same side of the equation, and I can condense these logarithms using my properties. And I know that when I see the difference of two logarithms, that is going to condense to the logarithm of a quotient, in this case, natural log of x plus 1 divided by x, and that's going to be equal to 1. So now I have taken my original logarithmic equation, got both logs on the same side equal to a constant, condensed those logarithms into a single logarithm, and now I'm ready to write this in exponential form. But I need to remind myself, and if you need to, go ahead and write this. It's log base e, right, of x plus 1 divided by x equals 1, isn't it? Natural log is just log base e. So you can say I'm thinking this, right? So now when I write this in exponential form, the base is e, the exponent's 1, and the result is x plus 1 divided by x. So what I need to do in order to solve this one is I'm going to multiply both sides by x, right? And on the left-hand side, I'm going to get e times x equals, on the right-hand side, these x's are going to divide out, and I'm going to be left with x plus 1. And I need to solve for x, right? So I need to get both those x's on the same side of the equation. And I'm going to accomplish that by subtracting x from both sides. So I'm going to get e times x minus x equals 1. And then I have still have two x's, right? And what I can do there is I can go ahead and factor out that common x. So I'm going to have x times, I'm going to have x times e minus 1 equals 1, because remember, after all, this is 1x, right? So I'm factoring out that common x, and I end up with x times e minus 1. If I distributed this, I would get x times e, ex, minus x times 1, 1x, right? All right, now I need to go ahead and divide both sides by e minus 1. And so I get x is equal to 1 divided by e minus 1. And I'm going to get a decimal approximation to this one. 1 divided by e to the first power minus 1 gives me two decimal places 0.58. So that is my exact answer is 1 divided by e minus 1, and this is my decimal approximation, right? And I need to check to make sure that this is going to be a valid solution. And recall that the way that I do that is I check that proposed solution in both of the logarithms. In this case, there were two, right, involved in this particular equation, natural log of x plus 1 and natural log of x. And my proposed solution is x equals 0.58, right? So again, I'm checking to make sure that this expression stays positive, right? Because I can only take the logarithm of positive numbers. So 0.58 plus 1 is 1.58, which is positive. And then, well, x is 0.58, right, which is positive. And so that verifies for me that this is a valid solution to my logarithmic equation in both its exact and approximate form. All right, now we know that when we were solving exponential equations, there were two methods, right, depending on what the equation looked like, right? If I could make the bases match, then I used the one-to-one property of exponential functions, and if not, I used logarithms, right? Well, likewise, for our logarithmic equations, we have two methods. The first one we've seen. If I can express my logarithmic equation in the form a single logarithm equal to a constant, then I can put it into exponential form and solve, right? But some logarithmic equations can be expressed in the form where I have a logarithm base b equal to another logarithm base b. And since logarithms are also one-to-one functions, we can use the one-to-one property of logarithms to solve. So what you're going to do is express the equation in this form, right, where you have a logarithm base b equal to another logarithm base b. And this form involves a single logarithm whose coefficient is 1 on both sides of the equation. And then you're going to use the one-to-one property to rewrite the equation without logarithms, all right? You are not dividing out logarithms. Don't even think that. You are using the one-to-one property. And then you're going to solve for the variable, and again, you're going to check your proposed solutions. All right, so looking at this first example, I see that I have log base 5 equal to log base 5. So I am going to use, and I'm going to write this all in caps, the 1-to-1 property. I'm going to spell it correctly too, of logarithms, to rewrite this as 2x plus 3 is equal to 3. So in other words, I am using the one-to-one property of logarithms to set these two arguments equal to each other. I am not dividing the logarithms away. I am not canceling the logarithms. So it's really important that you don't think that, because later on in your mathematical career, that can cause a lot of problems for you. Okay, so I need to solve this equation, and I'm going to go ahead and subtract 3 from both sides. And so I'm going to end up with 2x is equal to 0, divide by 2, and I get x equals 0 is my proposed solution, right? I need to check that proposed solution in both logarithmic expressions, and actually only the one, right, on the left, because it's the only one that involves a variable. So I'm checking to see for log base 5 of 2x plus 3, does a value of x equals 0, is that going to be okay for this logarithm? In other words, is 2x plus 3 going to stay positive for x equals 0? Well, 2 times 0 plus 3 is 3, which is positive, right? So x equals 0 is a valid solution to that logarithmic equation that I solved using the one-to-one property. Okay, so now let's look at example 24, and this is another candidate for using the one-to-one property, right? I'm going to copy this one-to-one property, and I'm going to bring it over here, because we're going to be using that again, right? We're not canceling logarithms. We're not dividing logarithms. We're not doing any such thing. What we're using is the one-to-one property to be able to rewrite the equation without using the logarithms. So on the left-hand side, I'm going to get 7x minus 12 because that's the argument to the logarithm on the left, right? And this is going to be equal to x, right? Because that is the argument to the logarithm on the right. So basically what we're saying is if log base 6 of 7x minus 12 equals log base 6 of x, then it must be the case that 7x minus 12 equals 6 because logarithms are one-to-one functions. All right, now I'm going to go ahead and solve this by subtracting 7x from both sides. So I'm going to get negative 12 equals negative 6x. And then I'm going to divide both sides by negative 6. And I'm going to get a proposed solution of x equals 2. Now I need to check that in both of my original logarithms, right? So log base 6 of 7x minus 12 and log base 6 of x. My proposed solution is x equals 2. So again, I'm looking at the argument and I'm checking to see, does it stay positive? So 7 times 2 minus 12, that's 14 minus 12 is 2, stays positive. And then over here it's just x, right, which would be 2, which of course stays positive. So this is in fact a valid solution to this logarithmic equation that I solved again by using the one-to-one property. Okay, last two examples for this section. And I'm looking at log of x minus 2 plus log of 5 equals log of 100. All right, so the first thing that I need to do is go ahead and combine these two logarithms into a single logarithm using my product rule, right? So this is going to be equal to log of x minus 2 times 5, right? And that's equal to log of 100. And then I can go ahead and distribute. And I'm going to end up with log of 5x minus 10 equals log of 100, right? And now I have the situation where I have a logarithm base 10 equal to another logarithm base 10. And then I can use, again, that one-to-one property, right, to rewrite this logarithmic equation without the logs. So I am going to be taking this 5x minus 10, and I'm going to set it equal to 100, which is the argument to the second logarithm. So I have 5x minus 10 equals 100. So first thing I'm going to do to solve this particular equation is I'm going to add 10 to both sides. So I'm going to get 5x equals 110. And then I'm going to divide both sides by 5, and I'm going to get that x is equal to 22. Okay? And then I need to check that proposed solution in my original equation, right? So I'm checking to make sure that if I plug in 22 to my original equation, it's not going to cause an issue for any of the logarithms, right? And I've been being very explicit and writing out in a very complete way my checks. But once you start to get more comfortable with this, you can, you can be a little bit less stringent about your checks. I'm checking to see if 22 as an input to this original equation is going to cause an issue for any of the logarithms in the original equation. And if I plug in 22, 22 minus 2 is 20. That's positive. That's my concern. So since 22 as a solution plugged into the original equation does not result in me taking the logarithms of any values that are not positive, then 22 is a valid solution to my logarithmic equation. All right, so for my final example, we're going to be looking at this logarithmic equation that involves natural logs. And again, I'm going to combine these two natural logs into a single logarithm using my product rule for logarithms, right? So this is going to give me the natural log of x minus 4 times x plus 1. And that is going to be equal to the natural log of x minus 8, right? I'm going to go ahead and expand or multiply x minus 4 times x plus 1. And when I do that, I'm going to distribute, right? And I'm going to end up with x squared plus 1x minus 4x minus 4. So I'm going to end up with x squared plus 1x minus 4x is minus 3x minus 4. And this is equal to the natural log of x minus 8, right? So now again, I'm going to be using my one-to-one property, right? So I'm not going to copy paste it again, but that's what's going to be making this whole show run, right? That's what makes it work. So I'm going to use the one-to-one property to rewrite my logarithmic equation without the logarithms. And so then I end up with this quadratic equation, right? If I go ahead and say, if the natural log of x squared minus 3x minus 4 is equal to the natural log of x minus 8, then it must be the case that x squared minus 3x minus 4 is equal to x minus 8. I've gotten a quadratic equation here, so I need to set it equal to 0, right? So I'm going to subtract x from both sides, right? And I'm going to add 8 to both sides. And that's going to give me x squared minus 4x plus 4 is equal to 0, right? And this will factor x and x, and two numbers that will multiply to give me positive 4 and add to give me negative 4, negative 2, and negative 2, right? So I'm going to get one proposed solution to this because x minus 2 equals 0 or x minus 2 equals 0 gives me the same result, x equals 2, right? And if I try to take this proposed solution of x equals 2 and plug it in to every single one of these logarithms in my original equation that involves that variable x, I'm going to see that it is not going to be a valid solution because 2 minus 4 is negative 2, right? And so that tells me that this solution is extraneous, and if it was the only proposed solution, that tells me that there is no solution. The solution is empty set. There is no solution to this particular logarithmic equation. And that is certainly one possibility when dealing with logarithmic equations, right? You could end up with valid solutions, you could end up with no solution at all, but you have to check. Okay, so just kind of as a summary for this rather large section, I've made kind of a flow chart for us in terms of solving exponential and logarithmic equations because there are some similarities between these two types of equations. When I'm solving exponential equations, I have two basic methods of solving. Logarithmic equations also have two basic methods of solving. And for both types of equations, one method involves using the one-to-one property, right? So with exponential equations, if I can make the bases match, right, then I can use the one-to-one property of exponential functions to solve, right? So if b to the m equals b to the n, then it must be the case that m equals n. And then just as a brief aside, let's consider a function that is not one-to-one, the quadratic. So if I know that x squared equals y squared, and the quadratic is not one-to-one, right? then do I know that x equals y? I most certainly do not, right? Because it could be the case that I have negative 2 squared for x and 2 for y, right? So it could be that x and y are both 2, right? It could be that x and y are both negative 2, but it could also be the case that x is negative 2 and y is positive 2. And then it would not be the case that x equals y. Just because I know that the outputs of a function that is not one-to-one are equal. In other words, they're both 4, right? I don't know which of those two inputs, negative 2 or positive 2, got me that value of 4, right? So just as a contrast to what does it mean, right, when I say because it's one-to-one, I can be sure that if b to the m equals b to the n, that m equals n, just think about, can you come up with an example of a function that's not one-to-one? And sometimes that can help you appreciate what it means for a function to be one-to-one, right? Okay, so likewise in our logarithmic equations, if I can, in a manner of speaking, make the bases match, right? If I can write it as a log base b of m equals the log base b of n, and the bases match, and I have two logarithms equal to each other, right? Then again, I can use the one-to-one property, this time of logarithmic functions. If b to the n, log to the base b of m is equal to log to the base b of n, well then it must be the case that m is equal to n, because logarithmic functions are one-to-one, right? Okay, so if I can make the bases match in my exponential equation, if I can write my logarithmic equation where I have one log equal to another and the bases match, then I can use the one-to-one property of those functions to then get rid of the transcendental nature of those functions, right? M equals n. And then solve those resulting equations that, for the most part, we've seen resulted in either linear equations, quadratic equations, or rational equations. Now, that doesn't have to be true, but for a college algebra class, that will be true. Okay, so suppose that the answer to those questions was no. In other words, I could not make the bases match in my exponential equation, or I could not write my logarithmic equation in the form where I had two logs with the bases matching equal to each other, right? Well, in the case of exponential equations, then I used logarithms to solve, right? I isolated the exponential expressions, right? And then I took the logarithm of both sides and then proceeded from there to solve, right? With the case of the logarithmic equations, if I could not create a situation in which I had two logs equal to each other whose bases matched, then I could write the equation in the form log to the base b of m equals c, and then write that logarithmic equation in its equivalent exponential form and solve, right? So there are some very similar characteristics of solving these types of equations, right? They both have two methods. Both of them are going to be using the one-to-one property if possible, right? Because that's always going to be the easiest way to solve if you can. But there is a very big difference between these two types of equations. For the exponential equations, there is no need for me to check my solutions, my proposed solutions for extraneous solutions or for solutions that are not valid, right? But with my logarithmic equations, I do have to check all of my proposed solutions. Right? The reason that I have to check my proposed solutions for my logarithmic equations is that they involve logarithmic functions, right? If I have f of x equals log to the base b of x, just my most general logarithmic function, my most basic one, right? The domain was that x had to be strictly greater than 0, right? Logarithms are not defined over the real numbers for arguments or inputs that are less than or equal to 0. It just doesn't make sense, because remember that base has to be greater than 0, and the result of raising any positive number to any exponent at all will always be a positive number, right? So it's not meaningful for me to even think about taking the logarithm of a non-positive number. And so as a consequence, I have to check my proposed solutions in all of the logarithms of my original equation to make sure that that my proposed solutions don't cause those arguments of those logarithms to be less than or equal to 0. Those arguments have to stay positive, right? So that is one of the biggest differences between exponential equations and logarithmic equations. And you need to be careful not to forget to check all your proposed solutions in your original logarithmic equations.